Alrighty, so we have taken a look at the concept of discrete random variables, and we have shown the formulas for computing the mean and the variance and the standard deviation of some arbitrary discrete random variable. For certain specific kinds of discrete random variables, like the binomial distribution, we can analytically sometimes work out a simpler formula than the more complex sum of values times probabilities kinds of stuff. In this next module, we're going to take a look at continuous random variables instead of discrete. And in particular, we're going to look at what's called the normal distribution and the uniform distributions. So, we want to be able to recognize when something is a continuous random variable, and we want to be able to do things like computing probabilities and computing means and standard deviations and so forth for the uniform distribution, as well as the same kind of thing for the normal distribution. There are many, many, many different kinds of important continuous distributions, but just to give you a flavor of what's going on, we're going to concentrate on just two, namely the uniform distribution, which is very simple, and the normal distribution, which is the most important kind of distribution in statistics for various reasons that we'll talk about. Okay, so a continuous random variable can assume any value in an interval. It's not restricted to, like heads or tails or 1, 2, 3, 4, 5, 6 on a die or something like that. If we have a continuous random variable, in an interval between 0 and 1, let's say, that means that the continuous random variable could take on any value within that range. And in particular, there are uncountably infinitely many values in this range between 0 and 1. Okay? No matter any two numbers that you select within this range between 0 and 1, you can find uncountably infinitely more values between that range of values. Or instead of a range between 0 and 1, you might have a range starting from 5 and going up to 10. Or you could even have a continuous random variable that selects some value in the combination of these two ranges. So the variable might take on a value between 0 and 1 or between 5 and 10. Okay? Now, we often, and I already suggested this when I was talking a little bit about finance and stock prices, we often use a continuous random variable to describe discrete random variables when the increments between the random variable possible values are tiny, so that the total number of possible values is huge. I gave the example of although stock prices on a stock exchange have to be priced in terms of pennies, we think of them as having continuous prices. Likewise, you might have somebody's income in rupees for some person or for some household. And again, although technically that's discrete, we would probably do our computations assuming it's continuous. So we don't have a probability mass function for a continuous variable. What we have instead is something called a probability density function, often abbreviated as a PDF. Here is, on the left side here, an example of a probability density function. let's suppose that the low end of this distribution is 0, and the high end is, let's say, 7. So maybe this peak here is at 2. Well, whatever. So we'll assume that the peak here is at 2. It's not appropriate to say that the value of this function is the probability of drawing a 2. And in fact, in particular, the probability of getting exactly a 2 in a continuous distribution is always going to be 0, which seems wildly counterintuitive, okay, unless you're really comfortable with calculus. Because although the probability of any specific value is always 0, the probability of being in a range near a specific value is always going to be some non-zero number, literally the integral of the density function between those two values. Okay, let me show you what I'm talking about. Let me draw an approximation of the same probability distribution. We'll say that this is 0, and we'll say that this is 7, and we'll draw this thing like that. Okay, that's that's a bad drawing. But here is our peak, and maybe that's at 2. We would never talk about the probability of x equaling 2, because that's going to be 0. Okay, that's not a useful thing to know. But the probability of being close to 2, that is, the probability that 2 minus some small delta x is less than x, which in turn is less than 2 plus delta x. This is meaningful. We can talk about the probability of being within a small range around x. Okay, so although we can't compute, well, although if we ask what is the probability of 2, that's a 0, we can compute what the probability is of being close to 2. What that means in this case, I mean, you know, the specific number that we get here is not going to be too relevant because it depends on the size we choose for our delta x. But let's take a look over here. Maybe this is 4.5. I don't know. Notice that the density function here is about half as high as the density function around 2. It's still going to be the case that the probability of x equaling 4.5 is 0, but the probability of being within an interval of delta x around 4.5 okay. All right, that's a really bad drawing, but the probability is the area of that around the value, and you can kind of see just by eyeballing my diagram here that although the probability of 2 is 0 and the probability of 4.5 is 0, the probability with being in a small interval around 2 is about twice as great as the probability of being in the same small interval around 4.5. So what the density is telling you is the relative probabilities of being near to the various values in the range. Okay, so we had some rules for the discrete probability random values, which was that for any given x, the probability of x had to be greater than or equal to 0, and that's going to be true here. In fact, the probability of any particular x is going to be exactly 0, and the probability of something happening is going to be the area under the curve, and that has to integrate to 1. Okay, in fact, those two properties are what define something to be a continuous distribution, that the probability of x is greater than or equal to 0, and if we integrate over the range of all the probabilities, the integral of all the probabilities has to be 1. Okay. The very simplest kind of probability distribution to think about is this one called the uniform distribution. That is, the probability is evenly distributed over some interval. The interval starts from C and goes up to D. Now, we have said that the area under the curve has to be 1 to integrate up to total probability of 1 that we're under that curve. Therefore, the height of this distribution, the value of the density function at every point within this range, is going to simply be 1 over d minus c. That is the end point minus the beginning point. Does that make sense? Sure. If the density function here is at height 1 over d minus c, and we integrate from c up to d, then we're going to end up computing the integral from of d minus c over d minus c is 1. Okay? The mean is simply half of the sum of the two endpoints. All right, we take c plus d, divide by 2, and that gets us the mean value in here. And without bothering to do a derivation, the standard deviation of this is d minus c over the square root of 12. You can, do the calculus to figure that out, but I'm not going to expect you to do that. And within a random distribution, the probability of being within any particular interval from a to b, all right, where a is greater than or equal to c and b is less than or equal to d, is simply the proportion of the size of that rectangle to the size of the overall rectangle, all right, which turns out to be just b minus a divided by d minus c. Let us try an example. So, we are working at a soft drink bottling shop, and our bottles of soft drink are supposed to contain 12 ounces. We believe that although our machines are set to put 12 ounces in each bottle, actually there's some variability in what the machines put into the bottles, and we believe that the machines actually dispense between 11.75 and 12.25 ounces inclusive in a uniform way. So any given machine is equally likely to dispense 11.75 ounces or 11.93 ounces or 12.07075 ounces or whatever. Any value within that range is equally probable. We're asking, what is the probability that less than 11.8 ounces is dispensed? Alrighty, well, let's see. So, our range is from 11.75 to 12.25. Okay, so that's our range of possible values. And we claim that we have a uniform distribution in here. The difference between 12.25 and 11.75 is 0.5. So in order for the area of this to be a total of 1, that means that the height here, f of x, the density function, has to be, well, let's just do it logically. If the width of the interval is 0.5, the height has to be 2, right? And does that make sense given the formula that we've been given? Well, the height should be 1 over 12.25 minus 11.75, which is 1 over 0.5, which is indeed 2. All right, so the density function across this whole interval is 2. The probability that less than 11.8 ounces is dispensed is the area of this rectangle over here from 11.8. And consequently, the probability of that is going to be 11.8 minus 11.75. That's the width, divided by the width of the entire range. Okay, in other words, this is the b minus a over b minus a over d minus c. All right, here's c, here's d. C is also a, and this is b. So b minus a over d minus c, in our case, is 11.8 minus 11.75 over that, and that's going to be 0.05 over 0.5. So in other words, that's going to be 0.1, so 10%. So there's a 10% chance that our machine is dispensing. There's a 10% chance that in any given bottle, the machine might be distributing less than 11.8 ounces. All right, so that is the uniform distribution. Next, we're going to take a look at the most important distribution in statistics, which is this thing called the normal distribution, also called the Gaussian distribution because it was discovered or described by the mathematician Gauss. The normal distribution is the foundation for doing inference, which, once we have learned all about probability stuff, we will get into doing inferential statistics, testing hypotheses and so forth at a more sophisticated, much more sophisticated level than the descriptive statistics we looked at before. So that's one reason why the normal distribution is so important, is because we use it for inference. Another reason that it's important is just we notice in the world that many continuous random processes do follow an approximately normal distribution. People's heights, if you look at the height of men or if you look at the height of women, they are approximately normally distributed. If you look at the scores on an aptitude test for employment, similarly the scores on an IQ test, those tend to be normally distributed. If you look, and I don't have first-hand knowledge of this, I guess, but apparently the daily demand for blood for doing transfusions at the Pittsburgh Blood Bank is normally distributed. There's a common typical level of demand. Occasionally there's very little demand. Occasionally there's a very great demand. It turns out that the normal distribution can be used to approximate some discrete probability distributions as well. And in fact, we will, in the next module, talk about the central limit theorem. Sorry, had a momentary brain glitch there. The central limit theorem, which demonstrates that the distribution of samples from any distribution, the distribution of the sample means converges to a normal distribution regardless of what the underlying distribution actually is. Okay, so here is what the normal distribution or the Gaussian distribution looks like. It's often described as bell-shaped. It is symmetrical. One of the nice properties is that the mean and the median and the mode are all the same value. Now, although the normal distribution is usually drawn like this in a so that it looks kind of finite, in fact, the normal distribution does actually have an infinite range. So, technically speaking, regardless of where the mean is, technically speaking, in a true normal distribution, you can get values that are arbitrarily far above the mean and arbitrarily far below the mean, even into negative values in a true normal distribution. Now, although the normal distribution does have this so-called bell shape, the specific characteristics of the normal distribution, that is how tight the bell is or how wide the bell is going to depend on the standard deviation. And similarly, the center, the mean value, is whatever it is. All right. So in these three examples here, we have one normal distribution whose mean happens to be -4. Its standard deviation is pretty narrow, 0.5. And so the curve tends to be kind of tight around that mean. Over on the other side, we have a distribution that has a mean of 3 and a standard deviation of 1. That's more of what we think of as a standard shape for a normal distribution. And in the middle here, we have a standard distribution with a standard deviation that's thicker than standard, if you will. And so this distribution is a little lower and wider appearing than the other ones. So they all have the same basic bell shape, but how peaked they are and how spread out they are depends on the standard deviation. All right, I'm not going to make you memorize this thing, but here is the so-called density function. E to the x minus mean over sigma squared, all divided by 2, negative of that. And then in the denominator, we have this factor, standard deviation times the square root of 2 pi. Okay, cool. I'm not gonna, there's no intuition about this that I'm gonna try to convey to you. But in this equation, mu is the mean of the standard of the normal distribution. Sigma is the standard deviation of the normal distribution, and then these numbers pi and e are what you are, I hope, familiar with from some previous mathematics. Now, I already mentioned when we were talking about the idea of continuous probability distributions that we can't talk about the probability of some specific value, because the probability of getting some specific value is always going to be 0 for a continuous distribution. Like, for example, if I ask you, what is the probability that the outside temperature right at this moment is 76 degrees Fahrenheit? And you might be thinking, well, that's not really 0. It might be 76 degrees Fahrenheit. No, actually, it's definitely not, because the temperature is a continuous distribution. And although we tend to specify temperatures in full degrees, what we really mean when we say 76 degrees, intuitively what we're really talking about is that the temperature is closer to 76 degrees than it is to 75 degrees or to 77 degrees. So without being, we don't actually do this math in our head, but more or less we're saying when it's 76 degrees, we're really saying that, okay, it's somewhere between 75.5 and 76.5 degrees. And for the normal distribution, also, if we want to specify a probability, we have to talk about the probability between a couple of values. What is the probability of the value of x that we draw falling between some lower value a and some upper value b? And this is going to require us, technically speaking, to do an integral on this gory density function from a to b. Well, so what do? Well, you look it up. You use a tool to look up what the probability is, all right? It's not something that you can do by hand. You can fairly easily prove, easily I say if you are comfortable with calculus, you can fairly easily prove that this density function integrated over its entire range from minus infinity to infinity, you can prove that this distribution function does integrate to 1. So you can prove that it satisfies our requirements for a distribution, that the density is always greater than or equal to 0, and that the integral over the range is 1. But figuring out that integral between two specific values, you use a table, you use an application, you don't try to do calculus yourself. All right, so here is the aisle normal distribution widget. And in my case, when I first pulled it up, it popped up with these initial values. The mean is set to 0. The standard deviation is 0.01. And by default, the test that's selected is whether the random variable that we draw is less than or equal to 0. Okay? So x naught, in this x less than or equal to x naught is set to 0. Well, remember that the normal distribution is symmetrical. Consequently, the probability that a number that you select is going to be less than the mean has to be 0.5, because it has to be the same as the probability that that value is going to be greater than the mean. All right? So it makes sense that the probability that any number that we draw is less than or equal to 0 is going to be 0.5. In this probability density function diagram, the scale here is slightly misleading. The scale here is actually in terms of standard deviations, not in terms of values 1, 2, 3, 4. All right. So if you look at the curve here, you'll notice that almost all of the probability density falls between about -3 standard deviations and +3 standard deviations. That gets us to that empirical rule thing that we talked about of estimating what the maximum range is that contains almost all of the items, and then dividing that by 6 to get an estimate of the standard deviation. Okay? Another thing that's being shown here is the cumulative distribution function. This graph shows essentially the integral from -infinity up to x of the area of that probability density function curve. Now, the nice thing about the cumulative distribution function representation is that this vertical axis is directly readable as probability. And you'll notice that the cumulative distribution function crosses at 0.5, all right? So half of the probability in the normal distribution is below the mean, and half of the probability is above the mean. And as I said before, if you look at the change in level from about -3 standard deviations up to 3 standard deviations, that's almost all of the probability is within that range. Okay, it's, what do we say, 99.7%, I think, is in that range. Now, if we ask, let's increase our x0 up to a value of, let's say 0.1. Okay. That has moved over a little bit to the right. Let's increase it to 2 standard deviations instead. Okay, so notice that if I increase my x0 to 2 standard deviations above the mean, now I've got 97.7% probability of selecting a value that is less than 2 standard deviations above the mean value. I can also ask for probabilities of being greater than x0. So in this case, that's going to be 1 minus the probability of being less than or equal to x0. And I can also ask for the probability of falling in between 2 values. Here, let's try. I want to find out what the probability is of being between -1 standard deviation and 1 standard deviation. Okay, this is a number that you'll end up more or less memorizing. The probability of being within the range from minus a standard deviation to plus a standard deviation is about 68%, just a little more than 2/3. If we go from -2 standard deviations to 2 standard deviations, that gets us to just a little more than 95%. And as we've talked about, if we go from 3 standard deviations below the mean to 3 above, that's where we get our 99.7% probability from. Okay, so that is the normal distribution widget. All right, now you may find yourself working with a normal distribution that is not of the standard shape with a mean of 0 and standard deviation of 1. How do you compute, let's say, if your distribution's mean is 5 and standard deviation is 2, and what you would like to do is to compute the probability that you draw a number that's less than or equal to 7, how do you convert that into a standard form so that you can then use something like this normal distribution widget or look up a value in a table, because tables and calculators pretty much always are based on the idea of having a mean of 0 and standard deviation of 1 around the mean. Well, in this case, if my mean is 5 and my standard deviation is 2, I hope it's obvious to you that a value of x equal to 7 is 1 standard deviation above the mean. So the probability that we draw a value for this distribution that is less than or equal to 7 is going to be the same as the probability that we would get in a standard normal distribution of drawing a value that's less than 1 standard deviation, okay? So, in fact, what you can do is you can take your specific normal distribution that you have computed from your data and simply subtract its mean and divide by your distribution standard deviation to get something called a z-score, or an equivalent standard normal distribution score. All right, so if my mean is 5 and the value of x I'm interested in is 7, whether x is less than or equal to 7, and my standard deviation is 2, then x minus the mean over sigma is 7 minus 5 over 2, which is 1 standard deviation above the mean in a standard distribution. And so if I want to know the probability of being less than that, let me go back over here. Let me get my standard deviation set to 1. And I want to know the probability of being less than or equal to 1 standard deviation. Okay, and so there it is. The probability of, whoops, I misread this. Okay, we want to know what the probability is of being between 5 and 7. So that's 1 standard deviation above the mean. I'm going to have to go back to, all right, so let me use 0 as my lower bound, 1 as my upper bound. Okay, and so the probability of falling within this region that is 1 standard deviation above the mean is 0.34, as shown here. Okay, so that's the idea of the z-score. All you need to do is subtract, take your value of x, subtract the mean, divide by the standard deviation, and that will convert into the analogous probability for a standard normal distribution. Okay, now this next problem is an inverse problem. In the previous problem, let's just go back for a second, we started with some normal distribution that we computed from some data, let's say, that has a mean of 5, standard deviation of 2, and we were interested in knowing what is the probability of drawing a value between the mean and 7. We converted that to a standardized form. In this case, we're going to start by finding a z-score to satisfy the requirements that we want, and then we'll have to convert back from the standardized normal z-score to the actual shape of the normal distribution that we're working with. Okay, so large employers often like to use skills tests to evaluate potential employees as the very first filter in the hiring process. So let's suppose that on some test, we know that the results of that test are normally distributed, or at least very close to, and that the mean score on the test is 60% correct, with a standard deviation of 10% correct. The employer here wants to hire the best 20% of applicants. And so the question is, in order to hire the best 20% of applicants, what minimum test score should the employer establish? All right, well, the first thing we need to do, and in this case, we're going to use the critical value widget where we start with our probability and from that get the matching z-score. We want to only hire the 20% best applicants. We are looking for the top part of this distribution. This is a right-tailed test as opposed to a two-tailed test. And we're being told here that the z-score that will be the lower end of that top 20% is 0.8416, or just 0.84. All right, so we figure out that this z-score of 0.84 is our critical value. Now, just as we could compute a z-score from the value and the actual mean and the actual standard deviation, we can turn this around. We can multiply the z-score times the standard deviation and add the mean to get our minimum score. So we multiply the z-score times the standard deviation and add the mean and discover that we need to look on our exam for a score of 68.4% or better. Remember, 60% is the mean score, so therefore 68.4% is somewhat less than one standard deviation above the mean, and that's where the top 20% cutoff is. Okay, and this slide just shows what I did over here on my right-hand screen. Now, this critical values tool we'll talk more about, because we can do not only right-tailed tests and two-tailed tests for normal distributions, but we can also do tests computing critical values for what are called t-distributions, which we'll get to later. Okay. Okay, so let's take a look at this blood bank example. Daily blood from the Pittsburgh Blood Bank is approximately normally distributed. That is, demand for blood from the Pittsburgh Blood Bank is approximately normally distributed. On average, 50 units of type O blood are purchased from the blood bank each day, with a standard deviation of 10. And the question is, how much inventory of type 0 blood should we require to make sure that there's only a 5% chance that we will run short? In other words, what we're asking is, we want to make sure that there is only a 5% chance that we will be out of blood. And we're not concerned about having extra blood, having an excess of blood. We're only concerned about running out. So this is going to be a right-tailed analysis, and therefore the critical value, z, is 1.6449. We'll just call it 1.64. So now we'll go to our pencil and paper, and our z-score, 1.6449. Our z-score is 1.64. Therefore, the amount that we actually need is going to be that z-score times the standard deviation plus the mean. Okay, so that is the units of blood that we need to make sure that there's only a 5% chance that we're going to run out. Our average, we're told, is 50 units. Our standard deviation is 10 units, 1.64. So what we need is, okay, 50 plus 16. We really don't want to run short, so let's round that up to 17 or take the ceiling of that. And so this gets us to 67. If we have 67 units of type O blood on hand, then there is a slightly less than 5% chance that we will not have enough in stock on a given day. Okie doke, so that is that.